Welcome to the AP Physics lecture. This is going to be covering uniform circular motion. This is the kinetics and dynamics of uniform circular motion. So, we have been talking about acceleration linearly. Our average acceleration is defined by the change in velocity divided by the time taken to make this change. So we've seen it like delta v over delta t. It's a change in the velocity over the change in time. But that's mostly linearly. Here, this is how the car is, and it's flat, and it's going to the right. It's accelerating. A equals to 15 meters kilometer per hour per second, going to the right. After 1 second, it's at 15 km per hour. After a second, it's at 30 kilometer per hour. And then, but this is what happens when the acceleration is linearly. So what happens when it is in a circular object? So here you go. This is a velocity on a circular path. Notice that the velocity here is traveling around the path of the circle. The velocity here is the same value. So if this velocity is in magnitude is, let's say, 30 kilometers per hour, this is also 30 meters per hour. The length here is the same. But what is the difference between these two? It's the direction. So if we look here, we saw that the original velocity was pointing to the right. Then the second velocity was pointing slantedly down this way. So this is the first tangent line, and this is the second tangent line. There's essentially a difference here. There is a delta theta here. There is an angle difference here. We can actually compute the change in the velocity here. How? If you remember it from your vector problem, we saw that we can just subtract v2 minus v1. So it is essentially this arrow. If we drew this right here, this arrow is actually pointing towards the center of the circle. So the delta v is pointing in towards the center of circle. If that is the direction of the change in velocity, this is pointing towards the center. Therefore, the acceleration is also going to be pointing towards the center. So what happens here is that the change in the velocity that is occurring is pointing towards the center of the circle. The fact that velocity is changing, there is an acceleration. This acceleration that we talk about is called centripetal acceleration or radial acceleration. And the formula for that is given as AR equals to V squared over R. Sometimes you can see it as AC equals to V squared over R. And this is always pointing towards the center of the circle. All right. Let's give you a conceptual understanding here. If I had 4 Indy cars here and it makes a turn around a circular path, they are entering the turns at the same speed here. You're going to rank the cars based on who has the fastest centripetal acceleration and explain what direction is the acceleration in. We saw that the centripetal acceleration is equal to V squared over R. We saw that all these cars are going at the same speed, so we can ignore this. So we can say AC is equal to 1 over R. There is a inverse relationship between it. So If R goes up, AC has to go down. So this has the longest, the red car has the longest R. If it has the longest R, it has the slowest AC. This one here has the shortest R. Therefore, if R is small, then AC is going to be the largest. So, which car here has the fastest centripetal acceleration? It would be ranked in this order. It would be orange is first, this is second, third, and this is fourth in terms of their centripetal acceleration. And we know in what direction. We saw that it's always pointing towards the center. A couple facts for the centripetal acceleration. One, the acceleration vector always points to the center of the circle when v is constant. The velocity vector always points in the direction of the motion, which is tangential to the circle. What I mean by tangential is that here the velocity only touches the circle once. That's called the tangent line, always once. And I draw the box here to indicate a 90 degrees because the velocity, which is the green arrow, and the orange arrow, which is the acceleration pointing towards the center, the velocity and acceleration vectors are perpendicular to each other at every point in the path for uniform circular motion. Centripetal motion is described using two ways. We first talk about the frequency, and we see this as the number of revolutions per second. How many times it goes in the circle. Okay. Then we have the period. Period is the time required for one complete revolution. There's a relationship. The period is equal to 1 divided by the frequency. So, the example. If the ball spins at 5 revolution per second, all you have to do to get the period is to put 1 over that. So the period would be 1 divided by 5 seconds to complete one revolution. No one really writes it as a fraction, so you will see something like 0.2 seconds as the period. A unique thing about this is that you can actually multiply f to the other side. So frequency times period is equal to 1. When two values multiply together to equal to 1, you would call these, this can be the regular element, and this can be the inverse element. Okay, frequency and period are inverses of each other. Now, once we understand the idea of frequency, which is revolutions per second, and period, which is the amount of time, seconds, a typical question would be, what is the velocity formula of a circle? The velocity is how fast you can complete going around this circle. But we know that velocity by definition is the distance over time. So, okay. The distance. What is the distance around a circle? Well, the distance around a circle is 2 pi r. This is the distance around a circle. No one really writes distance of a circle. What's another word for distance? It is the circumference of a circle. So the 2 pi r comes from the circumference of the circle. That is our distance unit. And the time is not t, this is the period. Because period gives us the time required for one complete revolution. A typical problem with circular motion. You see the student here is swinging a ball on a string above her head in a horizontal circle. A 50-kilogram ball at the end of a string is revolving uniformly in a horizontal circle of radius 0.4 meters. The ball makes 2 revolutions in 1 second. The question asks, what is the velocity of the ball? What is the acceleration of the ball? We saw here that the velocity is equal to 2 pi r divided by the period. We know that the time is equal to 0, not time, this is radius. We know that the radius is equal to 0.4 meters. We just need the large t, which is the period, which is 1/2 per second. How did I do that? This is the frequency. So the period, which is t, is just going to be the inverse of that, 1 divided by 2. That's how I get this. But no one really writes 1 divided by 2 seconds. You will see this as 0.5 seconds. Now we can just plug it in. We saw that the velocity is 5 meters per second. In the picture, we saw that at any point in this circle, there is a tangential velocity that's going at 5 meters per second. Here, there's a tangential velocity at 5 meters per second. Here is 5 meters per second. This is 5 meters per second. And the fact that the velocity is changing directions as it goes around the circle, there is a centripetal acceleration. Okay. Let me repeat that. Because the velocity is changing directions as it goes around the circle, there is a centripetal acceleration. And it is defined by, you can see it as AC or AR equals to V squared over R. You plug in the values, you get the answer. So the 62.5 meters per second squared is the centripetal acceleration, and this goes towards the center of the circle. Now the question is this. If the radius is doubled to 0.8, but the period stays the same, what happens to the centripetal acceleration? Well, what students did here is they just plug it back in. So now they did this problem, but now with a new radius. So they plug in here, they take this out, and they plug in 0.8, and they got a new velocity. So it's 2 pi times 0.8 divided by 0.5. Okay. They got the new velocity here as 10.05. Okay. Then they plug it in here. This is 0.05 squared. Then they divide that by the new radius, which is 0.8. And they saw that the new one, the new acceleration was 126.33. How much did it change by? So they did so the new AC was 126. The old AC was equal to 62.5. They divide this. So the new one is 126. Divide this by the old one, 62.5. And they saw that the delta here, the change, was equal to a factor of 2. Okay, so all you have to do here was just divide it. Okay, and you saw your delta was 2. So the answer here was 2. We saw that if you double the radius, the acceleration will essentially also double. Let's look at the forces in a uniform circular motion. We know that because the velocity changes direction, there has to be an acceleration. And the acceleration is always towards the center of the circle. Because there is always a acceleration. If there's a mass there, there's a force. So figure 5-4 shows a force is required to keep an object moving in a circle. If the speed is constant, the force is directly towards the center of the circle, which is the centripetal acceleration. A circular motion object always have a centripetal acceleration. Therefore, based on Newton's first law, forces are applied to it. An object moving in a circle have forces applied to it to keep it moving in the circle. That's Newton's first law. So you will see this as F summation of FR, or you could see it as FC. Doesn't matter. That is always equal to mass times acceleration. But this is in a circle, so you're going to see this as FAC, centripetal acceleration. And you could make that substitution because we note that AC is equal to V squared over R from our previous slides. The summation of FR or FC is called the centripetal force. Some disclaimer. The centripetal force here is not one force. It is a summation of all the other forces in this circle. 2. If you describe the direction of the net force, it describes the direction of the net force needed to keep the object in a circle. So a typical question would ask, what is the purpose of the centripetal force? The purpose of the centripetal force is to keep the object in a circle. Why do objects stay in a circle? Like in this situation? It's because of the centripetal acceleration. It is due to the centripetal force. So what is the centripetal force in this carnival ride? You see people hanging and they're swinging. Okay, it would be the tension force, which is on the rope. All right, that's the T. And then pulling them down is the force of gravity. That is the centripetal force here. What about if it's a planet revolving around the sun? Or in this case, the moon revolving around the sun. In this case, it would be the two masses. Okay, there is a force of gravity pulling the moon to the earth, and there is an opposite force of the moon on the planet. Sometimes it could be even in an electric field. If you view a molecule using this model of an electron moving in a circular path, and in this class we believe that to be true, you could see that the electric field here is fighting against the other field, the magnetic field, and that is what keeps it in a circular orbit. Okay, this is, I'm going to put a star next to this. You're never going to be asked about this question on the AP Physics 1 exam, and this is 50% true. Okay, there is, as you study more physics, you're going to get a better picture of this. So don't take this as 100% fact. So we saw that all the centripetal forces are caused here, and it points towards the center of the circle. Right? It points towards the center of the circle right here. The centripetal force points towards the center of the circle. So what keeps it away? So here I would normally show a picture of a hammer throw. Let me bring that up for you to see. What you're going to see here is that you're going to swing a hammer in a circular path, and look at the net. There's an opening only to the straight of the athlete. So let's look at it. Swing, swing, swings, release. And once you release it, it goes directly straight. Why? So that video should motivate this idea. Which path will the hammer follow when the athlete let go of the string? when the hammer is at point P. Notice that the net was going this way, and this way, and this way. Right? That was sort of what the net looked like. It was only open in front of it. Yes, you could actually guess. It traveled the path of point D. Okay. The hammer went this way because that's where the velocity was. Right? The velocity was tangent. Okay? And it is perpendicular. This is a perpendicular sign to the centripetal acceleration. So what was pointing down here was AC. The velocity was perpendicular to that. Right? So the object will actually travel straight to point D. There is nothing now causing it to continue its circular path. Originally, it should have continued to path F if the person kept holding on to the string. But once the person let go, it travels its tangential path. Many students will think, what about A, B, or C? Why doesn't it swing outwards? This outward force is called the fleeing force. And some people call that the centrifugal force. There's no such thing as this force around a revolving circle object. So if you swing a ball on the end, the two forces that interact is the force on the hand exerted by the string, as well as the force of the ball exerted by the string. When you let go, it does not swing outwards. This never happens. It does not go out. What happens is that it continues the path of its velocity. And again, the V here, the V is perpendicular to AC. So right here, this was AC pointing this way, and this was V. All right, there you go. That is everything that you need to know in terms of conceptual ideas about centripetal acceleration and the during uniform circular motion.